So, welcome you all. So, in this lecture I already talked about in my earlier lectures the notion of mixed derivatives, Hessian. So, now I am in a position to talk about mean value theorem and Taylor's theorem for functions of two variables, and I will just give one examples of Taylor's theorem. So, that is the plan. So, I will start with the notions of mean value theorem. That mean value theorem you know in the single variable calculus. So, what should be the appropriate notions in the context of several variable functions, and you know the notions of Taylor's theorem for single variable calculus and what will be the appropriate notions of Taylor's theorem in the several variable calculus. So, that is my plan for today's lecture. Okay. So, as I said, or as I promised, that I should talk about, or I should start with what notions of mean value theorem in the context of several variable functions and the notion of Taylor's theorem. So, let's start with that. So, what is mean value theorem? Of course, in the case of single variable, what is mean value theorem? If you remember, if I have a functions from say closed interval a b subset of R to R, what is the mean value theorem? So, you can have that if my function is, suppose some nice condition is there, suppose my function is differentiable, then if you remember, the kind of mean value theorem says that fb minus fa, if my function is, suppose a nice function, differentiable functions, derivative is continuous, everything, suppose very nice condition is given, then fb minus fa is exactly equal to derivative of f at some point xi times b minus a, and xi is a point in the open interval a b. So, that means given a functions f from closed interval a b subset of R to R, suppose my function is differentiable, then fb minus fa divided by b minus a, which is nothing but derivative at some point xi, and where xi is coming from the open interval a b. That is kind of statement you might have seen in case of real variable functions. Now, you know for several variable functions, if I have a function from Rn to R, then of course no such kind of division makes sense. So, therefore, this kind of things will not be true. So, then the question is what sort of things will be true. That means in single variable calculus we have the quotients fb minus fa divided by b minus a. That will not make sense in the case of functions from Rn to R. I mean, you have to think about that well. fb minus fa is nothing but derivative of f at the point xi times b minus a, but in that case that right hand side, instead of quotients, if I think about just this equality is same as derivative at the point xi times b minus a, then in that case if I have a functions from Rn to R, then what the right hand side, the left hand side fb minus fa, what will have? If I have a functions from say Rn to R, the value of the functions fb minus fa will be of element in R. The right hand side it should also give the element in R, but what is the derivative? Derivative, if I have a functions from Rn to R, you know what is the derivative, it is a vector, right? F is a function. So, f prime of xi is a vector, b minus a again it is a vector. So, but in Rn you know the concept of dot product, and in terms of dot product you can have the notions of mean value theorem, and that exactly it is there. What it says? It says that let f be a function from some set A subset of Rn to R. I assume two parts, one S is open and S is convex. Open sets you know, convex set means if I take any two points, line segment joining these 2 points should also in that set. That is the meaning of convex set in Rn. So, if I have a functions from f from some set S subset of Rn to R, and suppose S is open and convex, if f is differentiable in S for any 2 points a b in S, okay. So, suppose I have this S subset of Rn, okay, and suppose this is convex, okay. So, I think this is not a proper picture, suppose this is my S, okay. What I am saying is that suppose f is differentiable, okay, on whole S. If I take point A and point B, I have take 2 points in S, and convexity means what? That means the line segment should also be in that set, that is there by definition my S is convex. Now, if I have starting with 2 points A and B, it says that there exists a point C here, that means this is my line segment, I am saying this is L line segment. There exists a point C in my line segment, so this is my point C, okay. So, then there exists a point C on the line segment L joining A and B such that this equality should be true. That means fb minus fa should be exactly equal to derivative of f at that point C, because C is a point in the line segment and hence it is a point in the set S, my function is differentiable. So, therefore, derivative at the point C makes sense times b minus a. Now, there is actually times means there is a time means what is f prime c? F prime c is a vector in Rn. B minus a, B is a point in Rn, A is a point in Rn. So, B minus a is also a point in Rn. So, this product means I am talking about the dot product. In other words, what I am saying is that derivative of f at c is nothing but the gradient vector of f at c, which is nothing but del fc, and b minus c is the inner product or dot product I am talking about. So, therefore, this is the corresponding statement. And now you see you can have the similarity of these functions, what you know from R to R, similar sort of things. So, if I have a functions from closed interval a b subset of R to R, you know that a b minus a p, which is nothing but derivative of f at the point j times b minus a, where j is a point in the open interval a b. The same notion I am having starting with the functions f from S subset of R into R. Here I assume that my S should be open and convex. Then what I am doing is that take any 2 point a b in that your set S, and since it is convex, the line segment L, which is joining A and B, is also in that set. What I am saying is that the difference between the endpoint, that means FB minus FA, can be written, or there exists a point C on the line segment L such that it is nothing but the value, that means difference between the value of the endpoint FB minus FA, which is exactly equal to your derivative at the point C times B minus A, times means here the dot product. In other words, you calculate the gradient vector of f at C, and you have a b minus a, you take the inner product, which is nothing but the value fb minus ab, which is actually the appropriate extension of mean value theorem that you are familiar with in the real valued functions of real variable. Proof is also very straightforward. So, what I have to do, somehow even if I am kind of setting from Rn to R, but anyway, I am comfortable, or I know the mean value theorem in the functions from R to R. So, somehow I have to kind of give, I am bring down the argument in the R to R case. I know the mean value theorem, and then I will have to prove it. So, that is what I have done it. Okay, I have written just a hint, not the full proof. So, what we have to do, so what is your hypothesis? Hypothesis is that f is a function from set S subset of Rn to R, S is open and convex, and it is given that f is differentiable. Okay, that is given. Now, what you do, you consider f auxiliary functions phi from R to Rn, that means Rn valued functions from real number. What is that? So, this is very nice functions. So, this is nothing but you have a Rn. In A and B are 2 points in S, that means in 2 points in Rn. So, this is nothing but the line joining A and B, or convex combination or line segment. So, that means I am saying that phi is a map from R to Rn, which is nothing but phi t is equal to 1 minus t A plus t times B. That means it is not a line segment, it is the line passing through the point A and B. So, that means since t running over R, this is one convex combination, 1 minus t plus t times B, and so t running over R. So, if that is the case, then it is a kind of line passing through the point A and B. So, this is a very nice function. So, it is a combination of A and B, right? And this function is a function from R to Rn, and this function is very nice. That means I am talking about, I want to talk about that it is differentiable functions. You can write it easily, because what is this? Because you can write it as a component function. Each of the component functions is a functions of t, nice function, combination of or polynomial in t, and each of the component is polynomial. That means this is differentiable, this function is differentiable. Is that clear? So, it is very easy. So, what is this? So, you just suppose if you write, say A is equal to say A1 A2 AN, right, and B is equal to B1 B2 Bn. Then what is your phi of t? Phi of t, which is nothing but you can write it 1 minus t times A1 plus t times B1, comma 1 minus t times A2 plus t times B2, and up to 1 minus t times An plus t times Bn. So, phi t is a function from R to Rn. What are the component functions? It is just a polynomial in t. Each component is a polynomial in t, and polynomial t are continuous function, differentiable function, infinitely many times differentiable function. So, therefore, my phi, capital Phi is a map from R to Rn. Each of the component function is differentiable infinitely many times. So, therefore, my functions capital Phi is a differentiable functions. So, now I have two things in my hand. One, by hypothesis f is a differentiable functions from Rn to R. I have an auxiliary functions capital Phi, which is a map from R to Rn, which is also differentiable functions. Now, I have already discussed, if my function is differentiable, then chain rule says that composition function is also differentiable. So, what I am doing is that now consider the functions gt, which is nothing but f composed with phi t. Capital Phi is differentiable, f is differentiable, then the composition function by chain rule, it is a differentiable functions, but g is a map from where to where? G is a map from, I am defining from 0 to 1. So, it should be a map from 0 1 to R, because phi is a map from R to Rn. So, phi of t is a vector in Rn, f is a map from Rn to R. So, f acting on phi 2 is an element in R. So, therefore, now I have a functions, given functions f, I have first introduced an auxiliary functions capital Phi, then I am defining a small function g, which is nothing but a compositions of small f and capital phi, which is a function from closed interval 0, 1 to r. And what sort of function is g is? It is a composition of two differentiable functions, and therefore my function small g is differentiable. So now I can apply my mean value theorem in the real variable or single variable case. Now I have a function g from closed interval 0, 1 to r, which is differentiable. Now apply the mean value theorem in the single variable calculus. If I apply the mean value theorem on g, then what will happen? It says that g1 minus g0, what will happen? This is derivative of xi, okay, times 1 minus 0, and that is nothing but g prime of xi. Okay. But what is g1? By definition, what is g1? Look, what is g1? g1 is nothing but f of phi 1. But what is phi 1? Phi 1 is, look, this is the function is given. What is phi 1? That means this is nothing but f of b. And what is g0? What is that? Means f of phi 0. And what is phi 0? This is nothing but f of a. So that means you have a g1 is equal to f of b, and g0 is equal to f of a. So therefore left hand side is nothing but this one, fb minus fa. So only the right hand part you have to take care. So that means I have only derivative of small g at the point xi. I have to somehow show that this is nothing but the derivative of small f at the point xi times b minus a. That's the only thing. But what is g? G is given explicitly in terms of small f and phi, and you know the chain rule, right? If the composition function is differentiable, you can also calculate the derivative. Not only you can say that my composition function is differentiable, but also you can have the explicit expression of the derivative of your composition function in terms of the given functions. So what will happen here? So g is given. So what is by chain rule, what it says? So derivative of g at the point xi, which is nothing but derivative of f at point phi xi times derivative of phi at the point xi. That's exactly the things, right? Now what is this? Now this is same as derivative of f at the point phi xi. Now phi xi is, what is this? So look, phi is function is there. So phi xi. So what is xi? Xi is a point. So xi is a point in the open interval 0 to 1, right? Because I applied the mean value theorem for the function small g, and this is the interval 0 to 1. So that means xi is a point from open interval 0 to 1. Once I have a point xi is from 0 to 1, so phi xi belongs to where? So phi of xi, it should be a point, since xi is a point in open interval 0, 1, phi of xi should be in the line segment joining a and b, and that I think I have said that it is L, if I say that L. So that means phi xi is a point in L. Okay. So xi is in open interval 0, 1. Phi of t is given. It is the line joining A and B. Okay. So what is my phi xi? Phi xi should be a point in the line segment L whose left hand point is A, or left, I think one point is A and another point is B. So that means if I have, so that means this is my, okay, I have already done. So this is my A, this is my B. So this is my point phi of xi. Okay. So therefore what? So therefore derivative of f at the point phi xi, which is a point in AB, that is done. That means in the L. So only part you have to calculate the derivative of phi at the point xi. But phi of t is given. So what is the derivative of phi at the point t? So you can easily calculate. So phi prime of t, which is nothing but, you just take the derivative with respect to t, and if I do that, this is nothing but b minus a. That's it. Because you have a function phi, this is a component function. What is the derivative of the component functions phi? Take the derivative of phi is nothing but the derivative of the component function, and derivative of the component function, if I calculate, this is nothing but b1 minus a1. So what is this? You can also calculate from here itself. So this is actually b1 minus a1, b2 minus a2 up to bn minus an, and which is nothing but b minus a vector, right? So therefore I have done. So that means what? That means left hand side g1 minus g0, which is exactly equal to b minus fa, and what is g prime of xi? Well, this is nothing but derivative of f at the point phi xi. Phi xi is a point in the line segment joining a and b. That means phi xi is a point in L times phi prime j. So that means I can write this is f prime at the point c times phi prime of xi. This is phi prime of t is b minus a. That means this is dot product with b minus a, and this is actually the case here. and that I have written actually in terms of the gradient vector, because f is a function from Rn to R. What is the derivative at the point C, which is nothing but the gradient vector of f at C, that you know. So, that means derivative of f at C, which is nothing but d1 f at C up to dn f at C, and which is nothing but gradient of f at C. That is the derivative, and times b minus a, this is the vector which I am writing actually the inner product, and that is exactly there. So, this is very kind of nice. So, the statement is that okay, if I have a functions f from S subset of R into R, and suppose my set S is open and convex, and suppose it is given that my function is differentiable, then mean value theorem says that if I take any 2 point a b in S, then there exists a point C on the line segment. First, you note that if I take any 2 point a b in S, because S is convex, the line segment fully inside in that set S, number 1. Number 2 is that once I have that information, then what I am saying is that I have the existence of one point C in the line segment L, such that f b minus f a is nothing but derivative of f at that point C times b minus a. What I have done, I am just with the hypothesis, I am starting with an auxiliary functions capital phi, which is a map from R to Rn, which is very straightforward map. So, I am just taking the phi of t is equal to I minus 1 minus t times a plus t times b, that means the line passing through a and b point. Then what I am doing is that since it is a very nice map, I first convince you that yes, that auxiliary functions phi is differentiable, because each of the component function is differentiable, okay. And then I am considering that, consider that I have two functions, one is small f, which is in the hypothesis, and then you have the auxiliary functions capital phi. Take the compositions. Composition is also differentiable functions, because both f and capital phi are differentiable. So, therefore, by chain rule, yes, it is differentiable. Not only that, I know the existence of derivative of small g at that some point, okay. So, therefore, I have a then out of function small f and auxiliary function capital phi, I have construct a function small g from close interval 0 1 to R, okay, and I convince you that yes, the function small g is differentiable. Then and apply mean value theorem for single variable calculus, and then I just calculate the left hand side and right hand side, and the left hand side, it just from the composition follows that it is nothing but f b minus f a, which is same as g 1 minus g 0, and right hand side the derivative of g at the point j, again I just use the chain rule, and I said that yes, this g prime of j, which is nothing but your derivative at the point C, where C is in the line segment, times b minus a, which is same as the inner product between gradient vector of f at that some point C, which C is lying, where C is lying between, or C belongs to capital L, or line segment joining A and B, times b minus. So, another form of mean value theorem I said, yes. So, this is another form, this is called mean value inequality. What it says? So, let f be a functions from Rn to R, where S is open and convex, again same thing. Suppose f is differentiable, if there is I assume some extra conditions, if there is a real number m such that, because derivative is a linear transformation, right, from Rn to R. So, that means derivative of f at x is a vector in Rn. So, therefore, I assume that extra assumption. What is that? The derivative of f at x norm, which is dominated by a fixed constant, and that should be true for all x, that is very important, okay. Since my function is differentiable on S, that means it should be total derivative, or derivative should exist at each point capital X in S, okay. So, I want that the hypothesis says that the derivative of f at x is norm, or I have to consider the norm, right, because it is an element in Rn. So, if the norm of f prime x is dominated by m for every x, then you will have this inequality. What is that inequality? That means absolute of f b minus f a, which is less or equal to capital M times b minus a. Actually, it follows from the earlier one. Earlier one, what we will have? Earlier one, we have the just assumption that f is differentiable, and what we will have? There you will have f b minus f a, which is nothing but derivative at the point C times b minus a, or this is a dot product, right. And what is C? C is a point in the line segment L joining, and which is a subset of S. Is given, right. In fact, this follows from the earlier. Why? Because now what is the extra assumption? Extra assumption that derivative of f at any point whose norm is dominated by m. So, in particular, C is a point in L which is subset of S. So, therefore, I can say that norm of f prime of C, which is also less or equal to m, because it is true for all x. So, in particular, it is true for C, and then you just take the absolute here, absolute, And what will you have to do? You have to perform the Cauchy-Schwarz inequality. So this is a vector, this is a vector, so this is less or equal to norm of f prime c times norm of b minus a, and norm of f prime c which is dominated by m. So therefore this is less or equal to m times norm of b minus a. So very straightforward. So that means once I have the earlier one, that means mean value equality, then I will have the mean value inequality. If I have this assumption, that means the total derivative norm is dominated by capital M for all x. That is important. So what you have the earlier one, because S is open, convex, my function is differentiable, you will have the earlier one, and you have to just apply the Cauchy-Schwarz inequality and assume that fact that norm of or total derivative is uniformly bounded by M, and then you will have this inequality. Okay. Once I have this theorem, there is another theorem I have written. So as a consequence of this theorem, so you will have this result. What I am saying that suppose you have a functions f from a subset of Rn to R, where S is open and convex. Look, what I am saying is that if f is differentiable, on top of that, that derivative should be 0 for each x, then f is constant. And it actually follows from the earlier theorem. So now what is your function? Your function f is a map from a subset of Rn to R. Okay. S is open and convex, f is differentiable. So therefore I will have the earlier theorem. That means if I have that, okay, norm of f prime x is less or equal to m, then I have this conclusion. Okay. But what is, I assume I have another assumption that derivative of f at x is 0 for all x. So that means what is the norm of f prime x? It is 0. Okay. So therefore if I apply this one, then what will happen? So if I apply this one, so or whatever the earlier theorem also. So that means you will have fb minus fa, which is nothing but, even if you apply the earlier one, which is nothing but derivative of f at the point c times b minus a, right? This will be true because by mean value theorem it says, because it satisfies all the hypotheses, because my function is defined on S is open, convex, f is differentiable. So therefore fb minus fa, if I take any 2 points, then it is convex, means line segment will be in the full sitting inside S, and fb minus fa, which is nothing but derivative of f at c times b minus a. Okay, and what c? C is a point lying in the line segment joining a and b. But what is this? This is given that derivative of f at x is 0 for all x. So therefore this is 0. So therefore this is 0. And what will imply? This is fb equal to fa. So therefore if I have a function f from set S subset of Rn to R, where S is open and convex, and if f is differentiable, you apply mean value theorem, you have a fb minus fa exactly equal to derivative of f at some point c times b minus a, but derivative of f at x is 0 for all x. So therefore this is 0, right hand side is 0, therefore you have fb is equal to fa, and therefore function f is constant. One note I have written that this result is true if I have S is open as connected also. If even I do not need convexity, even connected also allows you to conclude this theorem, because once it is convex, then it is connected, right? Because any 2 points I can join by straight line, it is already inside that set. But the converse is not true. I have given an example. So that means even if I have the functions f from a subset of Rn to R, where S is open and connected, I do not need convexity, but convexity is much more stronger assumptions. Then also this is true. That means if f is differentiable, then derivative 0 at all point implies f is constant. But if I assume I have the convexity, then you just apply mean value theorem or mean value inequality, whatever it is, then you will conclude that fb is equal to fa for any 2 points ab inside that S, and therefore f is a constant function. Okay, so I think I should discuss this theorem as well, because partial derivatives of f exist and bounded implies the continuity of f. If you remember, I have said that if kind of sufficient conditions for differentiability, if a given a function f from Rn to R, if all the partial derivative exist and continuous, then my function is differentiable. I think I should discuss that theorem there itself. That means instead of continuity, if I assume that partial derivative bounded, then what can I talk about that? Can I talk about the differentiability? You cannot talk about the differentiability. Nevertheless, I can talk about the continuity of f. Okay, not the differentiability, but I can talk about the continuity. So I think I should add this theorem. This is very nice. So look at the statement of the theorem. So let f be a functions from S subset of Rn to R, where S is an open set in Rn. I am taking a point x naught in S. So what are the hypotheses? All first order partial derivatives d1f up to dnf exist in a neighborhood nx naught of x naught. And if I assume that all the nth or first order partial derivative are bounded functions in that neighborhood, then I will say that f is continuous in that neighborhood. So that means instead of partial derivative exists, instead of continuity, if I assume that it is bounded, then I will talk about the continuity of f. This is one of the sufficient kind of conditions. Suppose if I have if I give some problem and if I say that okay, whether this function is continuous or not, to check the continuity of f, there are many ways. You can use the epsilon delta definitions, or if I have a functions from Rn to Rm component function, there are many ways you can check the continuity. One of those is this one. So given a functions f, say from vector valued functions with vector variable or real valued functions of vector variable, whatever it is, then you just consider the partial derivatives, okay, and ensure that yes, partial derivative. If I suppose if I want to talk about the continuity of f at some point, you just think about the neighborhood of that point, calculate the partial derivative if it exists, and if you suppose ensure that yes, all the partial derivative exist in a neighborhood of that point, along with it is bounded in that neighborhood, then you can conclude that yes, my function is continuous not only at that point but in a neighborhood of that point. So that is another sufficient conditions to check about the continuity of f. Okay. So now I am come to the concept what is called Taylor's theorem. Sometimes this is called the extended mean value theorem. So what is that? So so I should say something before that. So what is Taylor's theorem? Now Taylor's theorem, I think you are familiar with the functions in the single variable calculus. That means if I have a functions f from R to R or some interval closed interval a b to R, then I want a kind of expression of that functions around a point. Suppose if I have a functions f from say some closed interval a b to R, then what is the importance of Taylor's theorem? Taylor's theorem somehow it says that suppose you are starting with a very complicated functions f, okay, but I would like to see the behavior of my functions near a point, say some fixed point, say a. Okay, so then what can I do? Now Taylor's theorem actually ensures you to talk about the behavior of your functions near a point. In other words, actually it says that okay, so if you remember that your Taylor's theorem for single variable calculus, that means if I have a functions from closed interval say a b to R, and if I take a point inside that set x naught say a b, then there is an expressions of around the point x naught, so like f of x naught plus h, which is equal to f of x naught then h times f prime of x naught then h square by factorial 2 times. So this kind of expression I think you have known. So right, so again single variable, right. So like from a to a b to subset of R to R, then I think if I take a point x here, so I think or something, so f of I think x plus h or I think f of x plus h times f prime x plus h square by factorial 2 f double prime x, say x naught I should say. So take a point x naught here, okay. So on so forth, I think h to the n by factorial n f h h n f n x naught times some remainder term, if you remember. Okay. So that means in other words what I am trying to say is that like in single variable case, if I have a function f and if you know the Taylor's theorem, that means Taylor's theorem ensures you to get the behavior of your functions around that point, or in other words I should say that I can approximate my function in a neighborhood of that point via polynomial. So that means polynomial approximations are there. That means if I want to know the behavior of my function around that point, and if I have a say very nice approximation by polynomials, then I can say many things about my functions, functional behavior. So Taylor's theorem somehow says like that one. That means you know the behavior. Suppose if I start with a complicated functions and if I want to know the behavior of my functions around that point, so Taylor's theorem ensures you that yes, you can know your behavior of that your functions in a neighborhood of that point by approximating that functions or value of the functions around that point via polynomial. That is one of the major part. It has many applications actually, like in I should say numerical analysis or say differential equations. It has a very nice applications. For example, if I suppose you have a mathematical problem is some mathematical problem is given to you, and suppose you do not know the solution in the analytical solution, suppose you do not know, but I can talk about some approximating solution of that functions, right, of that problem I should say. Then how do you do that? Now Taylor's theorem, one of the powerful tool that will ensures you, suppose if something analytical solution of some problem is not there, some mathematical problem, but still you can give some approximating solution solution of that mathematical problem, and there Taylor's theorem plays a very crucial role. In fact, it's a very powerful tool to know the behavior of your complicated function that you started with in a neighborhood of that point. So that is what Taylor's theorem very useful, at least in the single variable case. Now the question is, I know the notions of derivative like partial derivative, total derivative, direct line derivative. So therefore, can I have the same sort of phenomenon in the context of several variable? Or in other words, I should say, for like in the single variable case, again another way of saying that importance of Taylor's theorem is that suppose you have a point x naught are your functions, and suppose you know the value of your functions at that point along with some derivative of some finite order at that point. So out of that, just by knowing the value of your f and the finitely mean derivatives of the functions at that point, then I can construct a polynomial, and I can construct a polynomial in such a way it actually approximates very closely the value of your f. That is very important. So that means just by knowing the value of your functions and couple of derivatives at a fixed point, I can talk about, or I can construct a polynomial, okay, and that approximate your functional value near about that point. So that means I can talk about the behavior of my functions f near about that point. So that is another important features. So therefore, in the context of several variable, that is also needed, right? Suppose if I have a functions, say from several variable functions from Rn to R, say Rn to Rm, and suppose I do not know, suppose I started with very complicated functions, but now if I say that, okay, so can I approximate that my functions in a neighborhood of that some point by some polynomials? If I have a function from R2 to R, that means I want to talk about the approximation of my functions in a polynomial of two variables. So can I do that? Because polynomials is a very nice functions. I know many properties of that, and if I approximate my functions, value of the functions in a neighborhood of that point via polynomials, then I can say many things about the behavior of my f. Or as I said, some mathematical problem, if I do not know the analytical solutions, then I can talk about the approximating solution. That is why Taylor's theorem plays a very crucial role. So I want that my function is, I know, or I should say that I know the notions of derivatives in the context of several variable functions. Then can I have the kind of Taylor's theorem in this setting as well? In other words, can I approximate my value of functions in a neighborhood of that point via polynomial? Or if that is the case, then it will be very, very useful. That means in some cases I can give some approximating solutions, or in that differential equation it plays a very crucial role. So that is why this kind of talk about the Taylor's theorem in the context of several variable plays a very crucial role, and that is sometimes called extended mean value theorem. I can talk about, and later of course it is up to, you'll see the statement I have given up to second order. So of course nth order I will give you. So what it says is that I am just stating the theorem. Maybe next class I will talk about, this is actually Taylor's theorem of order 2, I mean nth order also I will talk about. So it says that if I have a functions f from set S subset of Rn to R, where S is an open set, take a point A in S, and suppose you have a point H, H1, H2, Hn in Rn, such that the line segment joining A and A plus H lies inside S. So that means I have a set S, okay. I am fixing a point A, capital A, which is A1, A2, An, taking another point H1, H2, Hn, and what I want that, consider the point A and A plus H. That means I am perturbing my point A by H. That means I have a point A, capital A and capital A plus H. So and I demand that, okay, I assume that, okay, yes, the line segment should be also in that set S. Then what is my hypothesis? Suppose that first order partial derivatives dif exist and continuous. That is very important. So if the partial derivative dif exist and continuous, along with the second order partial derivative should also exist at all points in the line segment L. Okay. So that means I have a fixed point A, I have a plus H, 2 points in my set S. I want that line segment also in that set S. If all the first order partial derivative exist and continuous, along with the second order partial derivative exist at all points in my line segment L, then it says that there exists a point P which is A plus theta H. A is a given point, I have a point capital H, theta is running between 0 to 1. So that means A plus theta is some point in the line segment L joining A and A plus H, such that the value of f at A plus H, which is nothing but f of A, times this one. What is this? This is h is given h1, h2, hn, which is nothing but h1 d1. d1 means partial derivative of f with respect to x1 variable up to hn dn partial derivative of f with respect to xn variable at f at the point A, times 1 by factorial 2, you will have h1 d1 up to hn dn to the power square acting on f at the point P. Now, it is expected, right, because if you know the statement of Taylor's theorem, it involves the value of the functions along with value of the derivative, finite some order, value of the derivative at that point. So, that means it involves the derivative of f, okay, in the Taylor's theorem. So, that means if I want to talk about the statement of Taylor's theorem in the context of several variable, so I should expect that it should also involve the derivative of f. In particular, I have the notions of partial derivative, then it should also involve the partial derivative. So, that is exactly going on here. So, that means I am starting with my functions along with some assumption that first order partial derivative exists and continuous and second order partial derivative exists in the line segment joining A and A plus h. Then I am assuring you that yes, there exists a point A plus theta h, that means in the line segment L, such that f of A plus h can be written as f of A. Then you will have h1 d1 up to hn dn. I already explained h1 is the component of h vector capital H, and what is d1? It is nothing but the partial derivative of f with respect to x1 variable, and dn partial derivative of at the xn variable, and that has to evaluate it at the point A, plus 1 by factorial 2 times this one. So, this is the square. So, square means what? So, that means n is equal to 2 I have written. So, that should be evaluated at P. So, this is the statement of extended mean value theorem. So, that means if you remember the earlier one, I will have the first order. So, that is, this is the second order is coming, that is why it is called the extended mean value theorem. If I take n is equal to t, n is equal to 2, that means f of a plus h, which is f a, that means the first one. Second one is what? I have two partial derivatives, right? So, that means h1 d1 of f at a times h2 d2 of f at a, okay, right? And what about this one? Square, okay? So, square means since from n is equal to 2, that means r2 to r, that means I have only partial derivative with respect to x and with respect to y, that means I have d1 and d2. Now, h1 d1 plus h2 d2 whole square, that means what? That means this is nothing but h1 square, that means the second order partial derivatives with respect to 1 1, that means del 2f del x square of f at p, and then what will happen? So, this is actually mixed derivative, right? d12 and you might say that, okay sir, why it is d21. So, now what I assume, that means I am saying that, okay, if all the partial derivative exist and this operator d1 d2 actually is same as d21. So, that is the another assumption I am actually assuming here, okay. d1 d2 means d1 d suffix 1 2 and d suffix 2 1, that is why 2 times h1 h2. If you just open it up, it should be h1 h2 d1 2 fp and then h1 h or h2 h1 d21 fp, but the value should be equal. That means if I assume that they are continuous or mixed partial derivatives, the value should be equal. That means it boils down to 2 times h1 h2 at this. Second one is the h2 square d22 f at p. So, that means this is actually Taylor's theorem, or I can say that is extended mean value theorem. Mean value theorem comes up to first order derivatives. Here actually I am talking about the extra one, the second order derivatives. So, this is sometimes called Taylor's theorem, of course also known as extended mean value theorem, and I think in my next lecture I will talk about proper statement of Taylor's theorem. That means in fact also I will tell you that in case of several variable functions, how I can approximate or how I can know, or how I should say how I can approximate my functions in a neighborhood of that point via a polynomial. A polynomial approximation is there. That means there should be a remainder term and then the corresponding approximation is there. And in other words, I can say that, okay, I know the behavior of my functions around that point via polynomial. So, that's kind of explanation I'll talk about in my next lecture. I think I should stop here. Thank you.